right, today we're looking at lesson 11.3 and we're going to start with task 1. All right, so today we're going to rewrite exponential models. All right, so the first thing it says is explore equations of exponential models. An exponential model can be rewritten in equivalent forms to reveal new information. You can use this technique to determine the rate of growth or decay for a different time scale. The population of Tinytown is currently 4,000 and increasing as shown. So if you look in the picture here, it says that it's increasing at a growth rate of 3% per year. All right, so let t represent the time in years after the present moment. An exponential growth function f of t equals a times b to the t power can be used to model the population of Tinytown. Complete the description of the function. All right, so it asks for the initial amount and the growth factor. So if we look up here, it gives us the initial amount of 4,000 and it gives us a growth rate of 3%. All right, so we're going to put 4,000 here. And it says a growth factor. Remember, a growth factor has to be greater than 1. So we're going to change the 3% to 0.03, and we have to add that to to 1. So 1.03, that's our 1 plus our interest rate, okay? Which, remember, the b can also be 1 plus r, which is our rate. So in this case, that's what we're doing. All right, so it says what is the decadal growth rate for 1 decade? The growth factor d equals b to the 10th power. All right, so b is your base, so we're going to raise that to the 10th power. So if we pull up our calculator, all right, we're going to do 1.03, and we're going to raise that to the 10th power. And so that's going to be about 1.34. So it says to the nearest hundredth, so 1.34. And that says this means that 1 decade the population will grow by approximately, and you can see here that's 34%. And that's going to be for a decade. Okay, a decade is 10 years. All right, so now let t represent the time in decades after the present moment. An exponential growth function, g of t equals c times d raised to the t power, can also be used to model the population of Tinytown, where c is the initial population. C is like in the spot of our a, so that's our y-intercept or our initial value, and d is in place of b, so that would be our growth factor. Okay, so all they're doing is using different letters, but it's exactly the same function. Okay, so it says complete the description of this function using your result from part B. So if we look up here, part B, we got the decadal growth factor of 1.34. So it says what is the initial population? The initial population was 4,000. And our growth factor is 1.34. We found that in part B. All right, now it says what is the monthly growth rate? All right, monthly means we're going in the other direction. So there's 12 months in a year. All right, so it says let m represent the monthly growth factor. Then m to the 12th power equals b. The annual growth factor. Complete the following description. All right, so thinking about going backwards. So we have that 3%, and we're going to have to take 3%, and we're going to divide that up by 12 months. Okay? So it's going to be 0.0025. So the monthly growth factor to 4 decimal places. Now remember, we have to add that in to do 1, so it's going to be 1.0025. So 1.0025. This means that in 1 month, the population will grow approximately blank percent. So it would be 0.25% to the nearest hundredth. All right, remember when you go from a decimal place, this is a decimal place, to a percent, you move it 2 spots. That's why this became 0.25 and those 2 zeros dropped off. So anytime you go from a decimal to a percent or a percent to a decimal, you just slide the decimal 2 places. All right. Now let t represent the time in months after the present moment. An exponential growth function, h of t equals k times m to the t power, can also be used to model the population of Tinytown. So again, you can see this is ab to the x power. They're just using different variables, so don't let that confuse you. Where k is still the initial population, that's your starting amount or your y-intercept, and complete the description using results from part D. Okay, so K was your initial amount. That's just your starting amount. And now we're going to get the growth factor from above, which is 1.0025. All right, so what does this tell you? This tells you that you can do different increments of time. So we looked at time in years, we looked at a decade, and we also looked at it per month. And you can see that as it goes for a decade, a longer period of time, this growth factor is getting larger. Okay, when you look at a smaller increment of time, when we're looking at monthly, that the growth rate is much smaller. So it says, as the units of measure for time increase from months to years to decades, does the corresponding growth rate increase or decrease? And we can definitely say this increases for the very reason I just said. Like the longer in time you go, the steeper that growth curve gets, and the more it increases over time. All right, it says, suppose the population in Tinytown was decreasing at a rate of 2% per year. Which of the following functions would model the population? Select all that apply. All right, so if it's decaying by 2%, that means we're taking 2% away instead of adding 2%. So for in years, 1.02 is a growth rate. And if you subtract 2% from 1, you get 0.98. So the first correct answer here would be this one. And again, it's because it says was decreasing at a rate. Decreasing means now we're looking at exponential decay. Okay? All right, so it says in decades. All right, so for in decades, that means we have to take the initial amount and raise it to the 10th power. So we're going to take that 0.98. Let's raise that to the 10th power and see what we get. Okay, so that's going to be about 82%. So that's going to be this one here. So again, it's going to decay quicker the further you go, just like before it increased quicker when it was growth. So now it's going to decay even quicker. All right, so that's decades. The last two are in months. So in months would be, if this is how much it is per year, it's going to be less than that. See how this is getting greater the further you go away? It's going to be less than that. So the bigger number here would have to be this one, even if I don't look at it. But we can look at it mathematically. If you like to have concrete evidence here, we can do 0.98 divided by 12 months, and that's how it's determined in months. So it's going to be this subtracted from 1, so it's going to be 1 minus this answer here. And that is not the correct answer. So what did I do wrong? Let's see. Let's see, so it's going to be 0.02 divided by 12. Okay, so I just subtracted the wrong thing. So it's going to be 1 minus this answer. which is the 0.998. So that's this one here, which logically I already knew that, but I wanted to be able to show it to you. So you're going to take the 2% per year, and we know that there's 12 months in a year, so that's why I divided by 12. And then when it's decay, it's 1 minus your interest rate, where when it's growth, it's 1 plus your interest rate. So that should be the correct answer. And that is all for task 1. If you have any questions, please let me know.